Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but you know, I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah.
Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Well, thank you to anybody who's listened to our podcast and the one person apparently who reviewed us. We appreciate it. Check it out. We're, having a good time with podcasts. It's mostly lighthearted, kind of goofy. We tell some stories. We play stupid games and make really amazing dad jokes.
That's right.
And yeah, check it out. I hope that everybody enjoys our podcast. If you are listening, we appreciate it. And please take us away, Alex.
Yeah.
I've talked
and it is about electrochemistry. Well, welcome everyone to another episode of Ask Us Anything About Electrochemistry. I'm Alex Paroff. This is my colleague, Dr. Neil Spinner. And this is a time where on Fridays at 1 p.m. Eastern Standard Time, we try to answer any questions that you might have about electrochemistry. We get a lot of questions from webinars and YouTube comments and emails and phone calls. And we just figured this would be a good platform for coming online and asking us questions about your research, about a concept in electrochemistry that you might not understand, and that we might be able to help you with. So this usually lasts for about 2 hours. We're streaming to YouTube as well as Twitter, so you can also watch us on Twitter as well. And if you're on Twitter watching us, if you don't see anything or hear anything from us, we will definitely be looking for comments on Twitter to respond to. So just to keep that in mind. I'm just going through my boilerplate of things. So we're lasting for about 2 hours. The questions that tend to be the best, we are somewhere kind of in the middle between like something very extremely specific, like what's the activation energy of this like ruthenium hexamine complex or something like that, where it's super, super specific. We might not know the answer. And we also won't be very good at answering very broad or general questions like, what is cyclic voltammetry? Give me a 5-hour lecture on like the fundamentals of cyclic voltammetry. Probably can't do that. But if there's an aspect or an element somewhere in between those that you need some clarification on, or something seems confusing, this is the place to do it. Lastly, we apologize in advance if we mispronounce your name when you ask us a question. They're just YouTube names, so you could literally put anything. One person was a Pokemon one time, so we apologize in advance for any questions or any times where we mispronounce your name. Also, if you're watching this after the live stream, there should be timestamps in the description below for all of the questions, so you can watch us after the live stream and figure out like, oh, what question is of interest. And we actually talked a little bit ago about eventually making like a full list of every single question or group questions together.
I was just going to mention that.
Oh, you were going to mention that?
Yeah,
take it away.
I was going to. So this was like 2, 3, 4, 7, 500 weeks ago. I don't remember. Time is irrelevant. Someone
like 1 week ago.
It was like,
I remember you told me about a week ago.
I told you a week or 2 weeks ago. I don't know.
Maybe
it was a little while ago.
2 weeks.
Someone asked the question, like, what are all the questions that have been asked in these Ask Us Anything live streams? And I said, that's a really interesting proposition. I would like to categorize them. I think it would be interesting. I still have open questions for ourselves practically about how we provide that. So the short answer is that I'm doing this now. I'm in the process of going through all 30, almost 40 episodes at this
Yeah,
point,
that's right.
and categorizing every question, sort of adding different tags and categories for, so it's like eventually I imagine some sort of searchable widget or page or something where you can kind of say, hey, what are all the questions that folks have asked about EIS, right? And
Yeah.
you like click the EIS tag and it will list every question that's been asked, and it'll be a link to that episode, that video
Mhm.
at the appropriate timestamp. And so you can just link to episode 15 at 48 minutes where someone asked, what does a Nyquist plot look like? And that's
Yeah.
me answering it or something like
Mhm.
that. So that's where I'm going. I don't know what the time frame for this is going to be. We have other things to do, and I'm, I have to finish aggregating all of those data, and I have to figure out where to put it. I don't know if it will go on our website. I imagine it makes sense on our YouTube channel somehow.
Yeah.
Practically how, I don't know. It's like this, YouTube's
so
not
sure.
a place for text, it's a
Yeah,
video
that's right.
platform.
Yeah,
So
that's
anyway,
right.
I'm not positive how I'm going to bring that, but we are going to bring that somehow eventually.
Mhm.
And it's an unexpected problem. A good problem that we've had is that we're now on almost 40 episodes. We've been doing this for like a year,
Yeah.
and we appreciate everybody that keeps coming and asking questions. We had no expectations about this live stream, whether anybody would come ask questions at all. And I know that you have week in and week out to give us stuff to try to answer, and hopefully we've been useful for everybody and helped some people out, and we really appreciate your engagement. Without you guys watching us, we wouldn't be doing this.
That's
So
right. That's right.
the fact that everybody keeps coming every week and asking questions means we're going to keep doing these. And if people say, I don't think any of your answers are right and you're all stupid and I don't want to do this anymore, then we will fade into the
Yeah.
oblivion and we'll go away. But
That's right.
apparently you all appreciate this, or at least some people do. So we appreciate you. And because of that, I want to make this better. So I'm going to try to aggregate all those questions and provide that in the future. So look out for that.
Yeah.
Now,
absolutely.
that's a lot of blabbing. So the first thing to get to is that it looks like Santiago had a couple of questions that looks like if you're still with us, you typed just before we went live. So I captured those. I do try to check the YouTube event and make sure we don't lose any questions if they were asked before we went live. And so this is the first one here. So please take it away, Alex.
Yeah. So Santiago is asking, in supercapacitors, which is the OCP? What is the physical phenomena involved, and why is it necessary to measure it before performing CV experiments? Could you make a drawing about the phenomenon? So I think there's a lot here. I'll be honest, I don't know a whole lot about supercapacitors. I haven't studied them, and I will tell you as much as I possibly know just about regular capacitors and OCP and just some of the physical phenomena that might be occurring. So give me a second. Let me kind of share my screen, make sure that this is showing up. So I'm gonna do that. All right, and then I'm gonna just minimize the question. But we're basically talking about OCP. Like what is OCP? And in short, it stands for open circuit potential. And when I think about a capacitor, we usually like to use this diagram, sort of say this is the electrical symbol for a capacitor. And the capacitor generally consists of these two oppositely charged parallel plates. So one might have plus signs, positively charged, and the other one is negatively charged. Okay. And there's usually some kind of dielectric or something in between it, such that there's no charge transfer from one place to the, actually it would go the other way. So actually it would look a little bit more, if it was going to be a charge transfer, it would look a little bit more like this. You'd have electrons going here and you have an E minus, right? But that does not happen. So I'm going to use red to say that this does not happen. There is no charge transfer, no electron transfer from one side to the next. So that is what a capacitor is. Kind of physically, there's a lot of physical phenomenon associated with capacitors, but so that's what a capacitor is. The open circuit potential is it's kind of a passive measurement. So if I hook this capacitor up to a voltmeter, basically, if you were to hook it up to a voltmeter and just kind of measure the voltage, so if I do something like this and there's like a little dial, right? And I'm measuring the voltage. That's what the open circuit potential is. You hook these two like nodes up, one side of the capacitor on the other side of the capacitor, and this would be the OCP. Now, of course, you have an electrochemical cell. You have something else. Other things you may have like solution and electrolyte and all kinds of other things. So OCP normally contains a lot of other information about the system, but OCP usually it's really looking at the potential difference between one side and the other side. And if it's not a capacitor, it's like the working electrode and the counter electrode, or the working electrode and the reference electrode. Actually, OCP in a three-electrode system is really looking at the difference, like when you actually do the measurement between I'm pretty sure this is just the working electrode and the reference electrode. So it's a passive measurement of what the cell voltage is. And from a supercapacitor standpoint, my very limited understanding about it is that you're able to measure the state of charge because what was it? The charge is equal to the capacitance times the voltage. So if you if you have a specific capacitor that has a specific voltage and it's rated for some level, then you can figure out, oh well, how what's the charge? How much charge is accumulated on one side of the capacitor or not? And these things, and they can charge at varying degrees, varying rates. So when that's my kind of initial impression when looking at supercapacitors about why you would measure the OCP. You'd actually be measuring the OCP so that you're solving for this value and getting a sense of how much charge is being built up in your capacitor, in your supercapacitor. And so you'd want to do that if you're running cyclic, people do an OCP measurement. I always recommend people do an OCP measurement actually before doing CV of regular three-electrode systems for a very different reason. If you, by accident, didn't connect your electrodes, the electrode leads from your potentiostat to the cell, you'll get a wonky OCP measurement. Like you'll get 0 or you'll get like 10. You'll go to like the rails. Or if two of your leads short and are touching each other, then you'll also get like a super weird result. So I've always used OCP as not just a proxy for what the charge is on my supercapacitor, but like, did I connect everything correctly? Like, is something disconnected or not connected? And other people also look at the OCP to look at how stable the system is. Is the OCP changing as a function of time? So oftentimes you'll be able to see like, oh, the OCP, it's going down, or it's not like stable, and then eventually it reaches a stable point, and then that your electrochemical system's kind of at equilibrium. So that's a lot of stuff that I just said. I don't know if that exactly answers your question, but if you're listening, please like leave a comment or something in the chat, and we can try to address them if it wasn't clear.
Yeah, all of that is exactly what I was hoping you would say. The only other thing that I would add, and then we'll get to your second question, then move on to some of the other questions that are live. I see there's a few.
Yeah.
Was that the other thing with a supercapacitor specifically? A lot of times the CV that folks do with supercapacitors is a method of determining the capacitance itself, right? Because you have, again, I don't know why I'm incapable of memorizing this equation. The current is equal to the capacitance times the scan rate, or over the scan rate?
Times the scan rate. Yeah. dV/dt.
Yeah.
And I have a hard time remembering the integral, which is what I put down. The charge is equal to the
CV.
to the
right.
To C times V.
Yeah. Right. So in a cyclic voltammogram, for example, the current in amps, right, is equal to the capacitance in farads times dV/dt, which is the scan rate. So that's volts per second. And this is similar to the one you just showed, which is Q is equal to C times V, which is to say farads times volts, right,
Mhm.
is coulombs. Sorry for the thing about C here being twice. This is cool. This is capacitance. This is coulombs for units, right? This is the units are below the dotted line.
Yeah.
If this is confusing. So anyway, these equations are analogous because if you think about an amp is a coulomb per second. So that's where the only difference between these two equations is this seconds in the denominators, because coulombs divided by seconds. Now this equation is equivalent, right? So
Yeah.
just to kind of show you the similarity here, but just to further this point, and it's a brief thing that I'll mention in relation to that, is that if you find your OCP, is if and before you do your CV and you have your OCP is, let's say here, right? This is 0 current. A lot of times what you're doing is scanning just a little bit around OCP. So you're going plus, whatever, 100 millivolts, and then minus 100 millivolts. I'm just whatever number
Mhm.
happens to be. But the point is, a supercapacitor or a capacitor, generally speaking, is you're looking at a non-Faradaic process. So it's like right around OCP in theory. If you deviate a little bit around it, the only thing that's happening is capacitive effects, double layer capacitance, or the super capacitive, whatever. I don't know whatever the right terminology is here, but like, you scan a little faster and you get a bigger envelope, right?
Mhm.
And that's you're looking at the relationship here, right? The changing the scan rate, increase the scan rate, the current goes up, and you can get a relationship to solve for the capacitance. So basically, that's the other reason you might check your OCP as a means for figuring out the limits of your CV, because you want to do it where there's hopefully nothing really Faradaic or quote unquote interesting happening.
Yeah,
So
that's a good
that's
point.
the only kind of other bit to add about specifically related to supercapacitors. Okay, so the other question from Santiago that was asked again just before we sort of went live here was related to a battery thing, so I can address this really quickly. Is it possible to perform a CV or a GCD, galvanostatic charge discharge measurements, on a commercial AAA battery in a 3-electrode potentiostat? So the answer is yes. If possible, how to connect the electrodes. So first of all, the first clarification to make is that a commercial AAA battery is probably a primary battery, which means technically, actually, the answer is no. You can't do a galvanostatic charge discharge. You can only do a galvanostatic discharge. You're not going to charge a primary battery. It will leak and bad things will happen. Don't do that. But they do make, I suppose, rechargeable. There are some commercial rechargeable batteries, I think. I'm not sure if they make them in AAA size and what have you, but if it's a secondary, it's a rechargeable battery, then yes, you can do obviously charge and discharge. But if you just, if you buy a Duracell, yeah, I'm like product placement here. I'm not endorsing anybody. Nobody's paying me, but Energizer, Duracell, whatever. You buy a battery right off the shelf, and it has whatever, a volt and a half usually, or something like that. It's an alkaline battery, and you put it in your Xbox controller until it's dead or whatever you're using.
And then you lose whatever game you were playing.
Exactly. You definitely lose the game. Okay. So yes, you can do some tests on it. So like, for example, if your battery is a AA, AAA, or whatever, how would you connect your potentiostat? So you're going to have a plus side and a minus side. Usually the plus side is the one with the tab that kind of sticks out, right? On it. Usually I think that's the plus side. That is the cathode side. The negative is the anode side. The correct attachment from your potentiostat, move the question if it's in the way. I don't think it is.
I don't think it is.
Yeah,
no.
just in case.
Yeah.
So this is your potentiostat, and I'm going to use my company's convention for lead colors. If yours has a different one, you can obviously work that through, right? But the working electrode, and in this case, it's a working drive. Do we even have orange? I don't even think I have orange. I have to find it. orange.
Yeah, there's red.
And the
yeah.
working sense, usually these are shorted anyway, but just
Yeah.
for what it's worth,
Mhm.
your working sense will go to the cathode. And I'll draw the orange for good measure.
Yeah.
So these will be shorted. These are usually shorted together anyway. Sometimes there's one lead.
Mm-hmm.
Most modern potentiostats have separate leads for working sense, because if you need to do a four electrode measurement, you can separate those, but usually they're shorted.
Mhm.
So those go to the cathode, and then your counter electrode, which again with our potentiostat is green, and I can't do white because it won't see it.
Yeah, you
But
can use like
I'll
gray
use
or
gray, yeah,
something
exactly.
like that.
The reference line for our potentiostats is white. So the counter and reference lines will be shorted together, and those will be connected to your anode. Okay, that is the correct orientation and connection for a battery, whether it's this AAA battery we're talking about or any battery really. The cathode is the working electrode. The anode is the counter and reference electrode. So it's actually a 2-electrode setup, even though you have a 3-electrode, potentiostat with a counter. The counter and reference will be shorted together, connected to the anode. When you do this, you will get a positive voltage measurement, and so the galvanostatic discharge, but really it's the discharge that you're after. You'll have a positive voltage, so you'll have, whatever it is, 1.5 volts, and you can apply. Well, that's terrible writing. Apply, minus
Oh, good.
whatever amps, milliamps, and then watch the voltage over time, start to, it'll probably plateau for a while and then whatever, die. If you want to just discharge it forcibly
Mhm.
by applying a bunch of current for a while, I don't know how long it'll take, to be honest. A commercial AAA battery is meant to be used for a long time under relatively low discharge rate. That's why you
Yeah.
can put a battery into your video game controller or whatever and have it last for weeks or whatever, unless you're like a compulsive gamer and you play
Yeah.
9,000 hours a day, and then it probably dies every couple days. But
Yeah.
anyway, there's a hopefully relatively quick summary of how to connect to the battery and what you would do with your potentiostat. So
Nice.
there you go.
All right.
So
Moving on.
plowing ahead here.
Yeah. We have kind of a setup question from El Madi Salmi. So he says, I want to confirm the following. If I'm using 3-electrode setup and I found an oxidation peak, for example, at 0.6 volts versus silver chloride when doing CV, and to apply the same potential in a 2-electrode setup, I know that applying 0.6 volts will not be the same potential found when working in a 3-electrode setup. Yes, that's correct. Can I put the reference cable RE and the counter electrode cable, I guess, together in order to mimic a 2-electrode setup to know exactly what would be the peak potential when working with 2 electrodes? So this is actually exactly the picture that Neil had. Just replace battery with your electrochemical system,
Exactly.
and that would be the 2-electrode setup.
Mhm.
Now, it's correct that that's how you do a 2-electrode setup, but would you know whether or not would you know like the exact potential of the peak potential in your 2-electrode system? No. Like in your 2-electrode system, if you have connected the reference and the counter leads together to, say, a platinum wire, I mean, you're going to want to put it to something that can push some current through. You are going to be changing the potential of, the interfacial potential of that counter electrode, which means that your reference point is going to be changing throughout the experiment. So the 0.6 volts measured in a 3-electrode setup is only really good for that 3-electrode setup in terms of measuring the potential, just the thermodynamics of your oxidation reaction. But then switching over to a 2-electrode system, you now have a different reference point, and it's a changing reference point. So that's going to make it harder. But it'll probably be, generally speaking, kind of hopefully somewhat close to 0.6. You might have to go a couple hundred millivolts, but you will be in the same order of magnitude range when looking for when looking for that oxidation peak. But it will be different and it will change. And there's unfortunately no great way of getting around that. So hopefully that addresses your question. Let us know if you need any further up clarification on it.
Okay. So next, I think Arya has a question about DPV. So that stands for differential pulse voltammetry. And the question is how to optimize modulation time and amplitude in a DPV for sensitive result. So what I'll do first is I'll share a page from our website, actually. Again, another cheap plug here, but it is what it is. So we have, this is on our knowledge base on our website. It's just a knowledge base article on differential pulse voltammetry as a technique. And so again, just to kind of back up and give a background here, as Alex did with OCP and everything, the differential pulse voltammetry is a technique. It's like cyclic voltammetry, but the waveform is a little more complicated. Effectively, you are sweeping the potential from somewhere to somewhere, right? You go up and then down, or down then up, whatever it is, but it's not just a linear movement. You go up, back down, up, back down, up, back down. And so it's a pulse technique, hence the P in DPV. And those pulses are done with the reason for trying to effectively remove background current and background processes. And so as this relates to your question, first of all, I don't 100% know which of the things you're seeing on the screen right now you're referring to as modulation time. I'm kind of just talking more generally about all of it. So I'm interpreting your question as just sort of how do you adjust all the parameters? If you're referring to one specific, like how long you hold the top part or the bottom part, I don't exactly know. But your question more generally is a good one in terms of how do I adjust the parameters of DPV to get a good result, right? The short answer, which is a very somewhat unsatisfying answer, is that it's trial and error. Frankly, you have to sometimes just try stuff and see if you get something good, and then adjust as you go to clarify what you're looking for. But effectively, it's a good way to clarify a peak location. It's a good way to clarify, a peak height, for example. You have what sort of you can think of as an effective scan rate. Effectively the speed at which this baseline is moving up is a function of how long modulation, if you want, or whatever time you've spent from here, from here to here, here to here, and then how much that incremented is. It's not as clear as a CV where it's like 100 millivolts per second, because it's like you have a short time at this top here, a little bit longer time at this bottom, potential. So the total amount of time for each step is like this top plus this bottom part. So that there's that, right? And then how high you increment is up to you in many ways, right? How if you have a long dwell time but you have huge steps, it'll be like effectively a fast scan rate, but it's just because you're jumping up 50 millivolts at a time. You can spend like a millisecond at each of these, but only go up a millivolt at a time, and so it's actually really slow. So there's a lot of modulation of these parameters that will impact that. Now, generally speaking, the goal of a DPV is to have a relatively short, as you can tell by the sort of proportions of this plot here, you have a relatively short dwell time at the top, right? There's some explanation of the the equations here. You can read the article. I'm not going to really get too heavy into the mathematics now, but you're pulsing at your forward whatever potential for a short amount of time, just to get a quick measurement at that potential, let's say, and then dropping it down for a longer time to let it settle. So, this is all happening like relatively short, like millisecond or something like that time frame, but proportionately, that's a long time to dwell at the bottom. And so you're letting it settle for long enough so that that's a background current you subtract. And basically each of these up and then down gives you one measurement, which is like a differential current, hence differential pulse voltammetry. So the current that is monitored is the difference between the top and the bottom, usually at the end of each of these pulses. So it's like you pulse up and then you down and let it settle. Pulse up and then down, let it settle. And so the purpose of the down part is that it's the background. It's the current not that is from all background processes. And so the difference between those is like the current of interest. Now, when there's no Faradaic processes occurring, that difference might be close to zero, which is why typically a DPV will often look something like this, as I share my screen in the slowest possible manner.
It's all good.
It will often look something like this. If you think about it as a cyclic voltammogram, a DPV, if this is your zero line, it will often look something like this wherever there's a Faradaic process. And then when you go back, it will be exactly mirrored. You don't get that 60 millivolt kind of thing. This should be the same line. I'm not trying to draw a hysteresis here. I'm just a bad artist. So effectively, it's a way to clarify where this peak is. And that's the effect. It's the effect of subtracting. So it's like over here and over here, there's just like there's no Faradaic processes happening. So the effect of jumping up and then dropping back down is that you have some settling of the current here and then some settling of the current here. And even though they're different lengths of time, there's no Faradaic process. It's a quick setup of the double layer, let's just say. And so this current minus this current is basically zero. I know I've drawn them in different locations. I should have drawn them probably here. Like effectively, the difference of the current is going to be zero until I start having a Faradaic process. So it's like as I pulse up to this part, I have a real Faradaic, increase of my current dramatically from the Butler-Volmer equation. There's kinetic information happening. There's kinetic current. And then when I drop back down, even if it's during the kinetic process, I'm waiting long enough and it's settling out. So I'm getting rid of the background current. It's like this peak. It's a good way to get like peak current, like get a decent measurement of the peak current, right? And then I don't know how to effectively describe the potential you get. Actually, is usually clarified as well. Why they're the same front and back. Can you explain that? I actually don't know how to explain that properly. Why does the potential?
Why
like you don't get the 60 millivolt split. You know what I mean?
Yeah, you don't get the 60 millivolt split.
Something about because the 60 millivolt split's a Nernst equation, right?
The 60 millivolt split comes out of the Nernst equation. This is definitely a more I would say like kind of steady state thing. Most people actually do.
It's the differential current. Is the
maybe
reason.
It's because it's the differential current.
I don't know how to best explain that, so I guess I learn a little bit more. I guess I won't. The point is that the differential thing. Now, again, the last part I'll say about this, and we'll move on because I know there's other questions. How do you tune these? So basically, it's like you're trying to tune the length of the top part, right, to be somewhat in line with the kinetics of what you're studying. So it's like if this top part is too short, you won't. Sorry. Let me put it this way: if this is too long, you'll have too much settling. It's like you're trying to capture like pulse up like really quickly to get like a snapshot of I'm at this potential. What is my immediate like response, right? What's my Faradaic current if there is any? Mm-hmm. So it's like sometimes what you're trying to do is you're trying to modulate this time to be as short as possible. Sometimes you're up against it because you just have to have this duration of this pulse be the maximum, I should say the minimum like the potentiostat can do. It's sometimes it's like a millisecond or less or 100 microseconds or something, right?
Yeah. So there's I only know this because I've been hammering away at like chronoamperometry for a while. So one thing to keep in mind is I almost look at this as like little chronoamperometry like steps, except we're like subtracting different ones.
Right.
There's actually a sweet spot kind of in the middle of the pulse. So when you first step the potential, you actually have a lot of background charging current, right? So to completely charge the electrical double layer, it's like 5 RC. Like the time constant associated with charging the capacitor is like 5 times RC. That gets it to like 99.3% charged. So whatever your uncompensated solution resistance is, times the capacitance of your double layer, which is going to be unique for your situation, that is going to kind of set the lowest limit for how fast you can pulse, because you're not going to want that data, because you're going to have Faradaic current convoluted with double layer charging.
Yeah. So this right here is what he's talking about, this RC.
Yeah, the RC.
Basically when the Faradaic process, or you could think about it in terms of the uncompensated, like you said,
Yeah.
resistance times capacitance is time.
Mm-hmm.
And then, like you said, basically 5, I always think about it about 3, but somewhere between 3 and 5 times,
Mm-hmm.
that's roughly 99%.
Yeah.
That means it's settled. It's steady, it's settled. So it's like, if your time constant is a nanosecond, whatever, then almost no time is required to be settled out, right? But
yeah. So if you had like no resistance, very, very small, but that's also to say, if you were to take or collect a data point beyond that, then or within it, like if it was just a few microseconds and you took it within it, then your Faradaic current is convoluted with capacitive current. So you got to wait a little bit, but you can't pulse it for way too long. Like you can't hold it super long, because you could have convective effects like vibrations and stuff in your electrochemical cell. So you need to find a sweet spot that's maybe like 1 second, a couple milliseconds. And as Neil said, you have to play with it, because it's going to depend on your electrochemical system.
Yeah.
It's, if you have a big electrode or you have a very small, solution resistance, those numbers are going to change.
And so what you might want to do is an impedance experiment, if you can, right? Figure out what your uncompensated resistance is, if you have a potentiostat that can do that, and figure out what roughly the capacitance might be of your system. And so you can kind of get some of those measurements, as Alex just described, before you determine the timing. Otherwise, really, it's just trial and error. I mean, if you don't have that ability, or you're not sure exactly what numbers you're looking for, you're just going to play with those numbers, right? And see what you get. And to a certain extent, it's practicality, because you might plug in numbers and it's taking absolutely forever because your increment's too small.
Yeah,
that's right. It's like you're going up and down and up and down, but it's like taking forever to get from 0 to 500, whatever your limits are. It's like you might have to adjust those to get reasonable results. So I hope that's helpful. It's there's a lot there, obviously. To
got more clarification.
I know. To a certain extent, it's a crappy answer. It's like, well, just try stuff. It's like, you're looking for advice. I understand that. Yeah. So hopefully that's a decent explanation of it, and maybe gives you
you got a starting point. Find the RC, and then you know that you got to collect a data point that's there. Also, another nice thing is, if you are doing these little small increments, you might not need to hold it that far, because charging the double layer from like 1 millivolt to 2 millivolts is actually really, really fast. It's faster than just I have to wait so many microseconds. No, you probably don't.
So if you go up 25 millivolts and down 25 millivolts, you might need to hold it a little bit longer.
Correct.
But then your increment's bigger, so you can get there faster, because there's a lot there.
There's a lot of playing. So that is the process for optimizing your DPG.
So do all of that. Good luck.
Yeah, everything we said, just do it.
Do it all. Yes. Okay, and we'll move to the next question, because we talked about this.
What type of cell is most appropriate to measure polymeric proton exchange membrane, and what kind of electrode would be most recommended?
This one.
Yes.
This one right here.
Oh yeah, that's right. No, truly.
So actually, this is one example of a kind of cell that can be used for testing membranes. This is called a Lugan. What do we call it? Advanced Lugan membrane cell. Yeah. So basically, now the first thing I'm assuming is that your question implies you're trying to test the membrane itself for, I don't know, conductivity or whatever other properties, right? And so this kind of cell right here, as you can see, has 2 white frame pieces, and it sandwiches stuff in between. Okay. The way that this kind of a cell works is that it allows you to do a 4-electrode measurement. I'm going to try to draw it really quickly
Yeah.
for you as well. So you have a membrane, let's say Nafion, right? This is your Nafion. That's the most common ubiquitous proton exchange membrane. Excuse me.
Mhm.
Proton exchange membrane material. And so you're sandwiching it in between basically two cells. Okay, so there's like two O-rings. That this is the exposed surface area, and there are like two cells here. Okay, and basically they have. I'm just drawing a very crude diagram.
No,
here.
no, it's fine.
Okay,
I mean,
but basically what you have
hard to draw.
is, you have electrodes in here. You have two electrodes on either side, so you might have two platinum wires, and you also have. This is a bad drawing.
oh no, it's fine. It's
That's a
fine.
really
I mean,
bad drawing.
you're trying to draw in like
I know, like
effectively
3-dimensional
pic-
and a 2-dimensional thing. It also looks like two worms looking
yeah,
at
like
each
two
other.
little
on either
aliens,
side. It's
like-
like two aliens. This is a really terrible drawing. I'm very, very sorry. I'm a disgrace to the artistic endeavors of the
No,
world.
okay.
So you have two reference electrodes on either side as well. This is the key to it. Basically, you have two reference electrodes that you have a Lugin capillary. This directs the measurement basically as close to the membrane as possible, right? So what you effectively have when you do this kind of measurement is a distance between that where you're measuring between these two reference electrodes. So you're getting a potential measurement across this, and then effectively you do like a 4-point measurement. Okay, and you get a measurement of the conductivity is L over RA. So A is the exposed surface area. Okay, R is the resistance, and L is the distance. This is L. It's the distance between the two. So basically, what you're doing is you're getting measurement across a very short distance, facilitated by these long Lugin capillaries across the membrane, and you do like an impedance measurement or a very short cyclic voltammetry. You get a measure of the resistance. You have the exposed surface area, and you can get a measure of the conductivity. So that's what you're after. Is sometimes sigma. I guess sometimes it's like, was it C or something? I don't know. Usually sigma is the Greek letter that people use for this. But basically, that is the measurement in very, very brief. What people are doing. To measure membrane, properties. Let's just say. Okay.
Yeah.
So if you have a follow-up question about that, please let us know. If you're talking about studying the fuel cell as a whole, that's a different kind of architecture. I can talk about that, but that's the answer I would have for measuring the membrane itself. That's one example of how you might study membrane characteristics.
Yeah, very good. So Cigar Paul asks, what is the relation between overpotential and OCV, or open circuit voltage, or open circuit potential? So there, I'm trying to think if there is a
There's no real
an
relationship. They're
easy
different
way to
concepts.
describe it. Yeah, they're kind of, I think of them as almost two different concepts.
Yeah.
So overpotential is the potential beyond the thermodynamic minimum to drive a reaction forward. So if you have two species in solution and they're in thermodynamic equilibrium, and if you have like the Nernst equation or blah blah blah, and it's like 50-50 of both of them, to drive the reaction any one direction so that you have more of one species versus another. And when I say species, I mean an oxidized and reduced form of a reversible redox molecule. That's the overpotential. It's what's that potential to drive it forward, to get current to flow, so you get more of one thing than another. So that is what overpotential is. And overpotential is used a lot in the catalysis field, usually to describe like, okay, is my material more catalytically active or not active? It's like, well, it's maybe not very active because the overpotential is super high. I need to apply an extra 300 or 500 millivolts to get the reaction to occur or to work, especially at the same level of current as something that isn't that material. So that's how I think about overpotential. Open circuit voltage is something we talked about a little bit earlier. It's the voltage sometimes of the cell, and it's a representation of just what's the cell voltage just between these 2 points. Like a little bit of current passes and it moves a needle, and it just tells you, oh, what's the voltage. And it's that voltage typically for like a 3-electrode system. You are looking at really kind of like what the surface charge is realistically. Like if you have a different molecule with a different, a different, supporting electrolyte, you're going to change what the open circuit potential is because the species in solution govern the surface charge on the working electrode. So they're kind of two different things in a way. But I hope that answers your question. I don't think there's necessarily a direct relationship between those two. It's not like one's proportional to the other. So
Yeah, unless the E0 happens to be the same as OCV.
yeah, that's right.
In that case, your overpotential is the potential beyond or away from the OCP.
Right.
But that's only if those happen to be the same, which is not the case necessarily, or often or whatever.
Yeah.
So yeah.
Let's see. And I want to make sure we have gotten some questions where it's like follow-ups from previous questions. So we'll hopefully when we get to those questions, we'll just try to answer all of them one after another. Hopefully. So we have a question from Muhammad. Why reference electrode used? So I guess why are reference electrodes used? So this is similar to what we talk about like OCP. But reference electrodes are used to represent a stable reference point in an electrochemistry or an electrochemical cell. If you had a 2-electrode system and you apply some voltage, you're going to get some current to flow at the working and at the counter electrode. But you don't know, okay, well, is the current or the voltage of the system like more associated with one electrode or with the other electrode? And there's almost no way of determining that unless you have something in your system that is not changing. And that's what the reference electrode is. And the reference electrode is just a redox pair that has a consistent current. It's what's described as a supposed to be ideal non-polarizable electrode. The potential does not change even if a little bit of current flows through it. So that is why reference electrodes are commonly used, and they're mostly used for analytical experiments. And then I think he has kind of a follow-up, which I think is
I have some slides.
Neil's favorite topic, which is Tafel slope. And I think the question is, why is the Tafel like
what does it tell you?
What does it tell you?
So let me try to explain this. I'll go through these slides. I don't think it works. Tell me, you can't see the.
I can see. It
doesn't. For some reason, I need to figure this out here. When I. What is this?
It's not showing like
PowerPoint. It doesn't
view.
show the PowerPoint view. I need to.
Oh, you need to not have that X.
It's like I need to. I want to do this slide. You know what I mean? This is something I haven't figured out how to do with Restream yet, to be perfectly honest.
Yeah, no.
Okay,
no,
I'm gonna figure it out. I swear. But presenter view. So.
And then you have to.
I have to unshare and then reshare.
Yeah, reshare is the other one.
Do. So if I share it now, I think it works. I'm like, tell me, does this work?
Yeah.
Like this is like the presenter view for sharing. I don't
Correct.
know why it doesn't.
Yeah.
But anyway,
that's fine.
Okay, so I'll go through what the Tafel slope is, because it's partly how they answer your question. What does the Tafel slope show us? It's millivolts per decade of current. You've identified the unit properly, but where does it come from? It comes from the Butler-Volmer equation. So this is the Butler-Volmer equation. And the Butler-Volmer equation is a kinetic-only equation. It describes kinetic current, I sub k, sometimes you'll see. And it's related to I0, which is called the exchange current or exchange current density. It's sort of this fundamental property of your electrode. It's sometimes, as Alex will tell you very happily, it's better described by the exchange current. The exchange current. It's better explained by the heterogeneous rate constant, which you could extract from this kind of analysis. So the exchange current or exchange current density is kind of not all that necessary and not all that needed. It's not also really part of the Tafel slope, thankfully. So we'll plow forward without that. So basically what you do to obtain the Tafel slope analytically is we ignore one of these by assuming, if you recall Alex's just completed explanation of the overpotential, if we have a large enough overpotential, we effectively have less than 1%. This is for some perfect kinetic, thermodynamic, whatever process, whatever my E0 is. If I have a large enough overpotential in one direction or the other, I'm neglecting the oxidation or the reduction entirely, because it's only effectively 1% or less of that. If I have a really, really large overpotential positively, I have very strong oxidation happening and no reduction. It's fully irreversible. I can neglect one of these terms. Okay. So assuming I'm neglecting this one, you could do it for either way. It doesn't matter. Then this is basically what I get is the Tafel equation from which you get the Tafel slope. The Tafel equation is half the Butler-Volmer equation, and this is its form. So it's just these terms here. So this is the alpha is the symmetry, energy barrier. It's usually 0.5 for most reactions. Consider it 0.5. N is the number of electrons transferred. F is Faraday's constant. R is the ideal gas constant. T is the temperature, and eta is the overpotential. And I just told you I0 is the exchange current density. So to get the Tafel equation in a form where the Tafel slope is usable, we take the natural logarithm of both sides, or the log base 10 of both sides, however you look at it. When you do the log base 10, you end up with the log of E, to get it to log base 10, because we typically have decades of current, as you suggested with the unit there. Excuse me. So it's just easier to do than natural log, like millivolts per, natural log decade or whatever you'd call it. So we do log base 10 because it's easier to conceptualize. Okay. So the Tafel slope comes from the plot of overpotential versus the log of the current. And it's all this stuff. That's the Tafel slope. So the reason it has those units is because it comes from plotting potential, volts, millivolts, whatever, versus log of I, which is technically unitless, right? When you take the logarithm of a unit, it's sort of implied it's unitless, but that's why we say decades of current, because the logarithm base 10, it's a mathematical function, right? It's base 10. So decade is just a English word for, of every 10, whatever you want to call it, right? It's just metric system, every 10 kind of a phenomenon. Again, I'm sort of saying this because I know not everybody is a native English speaker, so I'm trying to hopefully help you understand this concept. It's a little more clear if English is your native language to kind of understand the concept of decade, perhaps. So I just didn't want to assume would be maybe obvious. But the logarithm of the current is, that's where it's, decade of current. So that's what we say decade, millivolts per decade of current. Whether it's milliamps or amps is irrelevant. And so what does the slope tell us? Well, it gives us information about this stuff. RT, alpha, N, and F. Log E is just a number. 1 over log E is about 2.3. So sometimes you'll see the Tafel slope written as 2.303 RT over alpha, whatever. That's just 1 over log E. That's just what that number is, right? E is 2.71828, blah, blah, blah. Okay. So what it's telling us is just kinetic information, effectively. It's giving us information about, is alpha 0.5? Is N 1? What was my temperature? I guess that's probably something that But the most common thing people are getting really is the N, is the number of electrons transferred. For things like the oxygen reduction reaction, people are looking for N to be 4. Okay. And basically you're looking for a deviation in this number, because if you plug in like the most typical numbers like alpha 0.5 and N equals 1, the Tafel slope is 118 or 120 millivolts per decade. So deviation from 120 indicates, usually that n is not 1. Okay. And you can just sort of generally think of the Tafel slope in terms of its units, millivolts per decade of current. So as I 10x the current, kinetic current only, again, this is just kinetic information. It's like as I 10x the current, what is the corresponding change in voltage of the kinetic process? It's telling you how the voltage changes for every 10x change in the current. So, I mean, again, that's kind of a giving you the answer in terms of the unit, but that's really specifically what it is. So hopefully that's a good, relatively quick overview. That comes from a webinar that I've given a couple times. You can see it on our YouTube channel. It's in a tier 2 members webinar playlist. You can see I did two full hour long webinars on rotating disc electrode analysis, Levich, Levich, and Tafel analysis, and I do some of that stuff in the derivation of the Tafel plot in the Tafel equation and everything. So that's a rough, quick overview of it for you. Hopefully that's helpful to you, Mohammed. Santiago had a follow-up.
Santiago has a follow-up. He says, thank you very much regarding the OCP question. I was referring to the system of an electrode submerged in, for example, N2O3 and measuring voltage versus time. He then has a follow-up, which is, why does the graph decay and stabilize over time? Is something happening with the charges of the electrolyte and the electrode surface?
Yep.
Yeah, absolutely. Absolutely.
The Cottrell equation, effectively, right?
Well,
I guess if you're applying a current.
Well, the Cottrell equation looks at the current versus time for a diffusion controlled species. He's just looking at the
the voltage.
The voltage.
Oh, I'm out the wrong unit. Yep.
But it's like when you like just put new electrodes right into a solution or you just stir the solution up, like there's a lot of like movement. Like the electrode may have stuff on the surface. There's always like stuff, and there's like some exchange that's going on. Like really, it stabilizes to establish equilibrium. And once it's established equilibrium, the open circuit potential should remain constant. But yeah, it's like all kinds of stuff are dynamically occurring. Sometimes very slowly. Like it might take a while before your electrode stabilizes and your OCP is actually like there and it's not changing, and you have an established double layer at the open circuit voltage, and that stuff can just take time as your system is just equilibrating. So that happens a lot. That definitely happens quite a bit. Let's see. Okay, so now going back up,
I think that
question from AB.
I think so.
Another?
I think that's the next one.
Next one is in a concentration cell, which is a type of galvanic cell. Yes. Do I need to put a reference electrode? And if yes, why?
So I think the answer is no. Mm-hmm. And if you do, the reason for putting a reference electrode is if you are interested in the individual potentials of the anode and the cathode. It's not always the case that you are interested in those. Quite often with a galvanic cells, this goes for fuel cells and batteries and sometimes capacitors and things like that. It's usually a 2-electrode kind of a system. Usually the amount of energy, the power, the energy density that you get out of a system like that is a function of the voltage, which is a direct potential energy between the 2 electrodes present, the anode and the cathode, right? So whether the anode is really somewhere crazy and the cathode is or is not also somewhere crazy, there's a voltage difference between those two at any given point, and that's usually just directly related to the amount of power, energy, whatever that you can get from that cell. So a battery has 1 volt between the cathode and the anode. It has some capacity, some amount of current that you can draw from it for some amount of time. That's enough. Like that's enough information. So everything Alex talked about before, earlier, about a half an hour ago at this point, about why would you use a reference electrode, right? We talked about OCP and that measurement versus AgCl. It's something because it's a non-polarizable reference that doesn't move, and so you're getting this this is my working electrode potential. This is its actual potential, with relation to a standard reference, and it's not changing, it's not moving. All of that. That's really only important when you're trying to study that one specific electrode and maybe its process and something about the potential it's at. But in a lot of these kinds of galvanic situations, you just care about the overall power of it, the voltage of the cell itself. So the reason to use a reference electrode is if you're trying to do some kind of a specific study of like a cathode material or an anode material, and you want to know its individual, the voltage of my cell is a volt and a half, whatever. But the voltage I want to see, so as I discharge it, it goes from a volt and a half down to half a volt, whatever. You're drawing current until you get down, and then you charge it back up, whatever the system may be. Does that mean that my cathode was at 2 and my anode was at 1, and so the difference is 1, and then as I discharge down, my cathode goes to 1.8 and the anode goes to whatever 1.5, and so now I have 0.3 left? Like, I mean, like, what's the difference is just whatever they are, they're moving at different rates. If you care about what each of those are doing individually, because it gives you information about it, then you're going to need a reference electrode. But quite often that isn't something that people are interested in. So that's the answer to why you would use a reference. And hopefully that illustrates to you why many folks doing this kind of research don't use reference electrodes, because you don't need to know that information quite often. You don't need to know specifically what the potential was at either electrode. You just need to know how the battery or the capacitor or the fuel cell, how it performed overall. Mm-hmm. So there you go.
Very good. Very good. Follow-up question from El Mehdi. He says, imagine I have an oxidation peak at 0.45 volts versus silver chloride. He did this CV at 5 millivolts per second, and then 0.55 volts at 100 millivolts per second. What is the right potential to choose if I want to carry out CA, chronoamperometry, and PS, IR compensation is already done during CVs? So,
first of all, I'm not imaginative, so I won't imagine this.
Yeah.
You can't make me imagine.
Imagine.
I
will try to imagine.
I don't want to imagine. I'm a very practical, down-to-earth person. You can't make me imagine something. I resent that.
So
I'm just teasing.
So one thing that is a little odd is that technically the oxidation peak, the standard potential, whatever it is, should be the same with IR compensation on, even at 2 different scan rates. And it's off by like 100 millivolts. So I am a little curious about maybe the solution resistance you may have chosen for doing IR compensation on this system. So that's one thing I would at least, maybe it's a separate issue. But actually, the voltage that you want to choose for chronoamperometry is probably going to be like maybe 700 millivolts or something. Like, you want to apply a voltage that is sufficiently high that you only have diffusion limited current. If you apply voltages that are slightly lower or at the redox potential, you're not going to have a good like diffusion limited current. So let me demonstrate this for you. It's kind of very simply, and actually I'm gonna just move your
I can hide the question.
If you just hide the. So this is our software. This is Aftermath software, and I'm gonna do a electrochemical simulation. So you can do this too on something called Aftermath Live, but I'm going to do a just a basic electron transfer reaction. We can actually put exactly the parameters that you have. Let's just put 550 millivolts. And let's say you've got a nice, very fast electron transfer rate going on. And then you've got a normal diffusion coefficient of like 1 times 10 to the minus 5, and then you start with 1 millimolar. And then if you do the same thing on your other species, the oxidized form. So this is just the electron transfer. And then if I chose bulk electrolysis, that's the same thing as chronoamp. Now, if you selected, let's say you selected 550 millivolts, and let's say you did it for like 10 seconds. Okay. Now, if I simulate this, and I'm going to move this over so you can see it, one thing I want you to pay attention to is the current at the peak right here. So you're getting a little over 4 or so like milliamps of current, right? But if I selected a higher, or not a higher E naught, but if I selected a higher potential to step, I would actually get a larger current. So if I simulate this, I'm actually getting way more current here. And I could keep doing this. Like I could keep going to higher and higher current or potentials, but you'll start to notice if I keep going higher, I all of a sudden it's like it's not going up anymore. Like I'm no longer getting anything higher than this. So, but if I had something even 600 millivolts, right? So if it's 600 millivolts, it goes lower, and if it's 550 millivolts, it's also lower. You want to pick a voltage that's way higher than the E naught or the standard potential of your system, because you're not going to be completely diffusion controlled or diffusion limited. You'll actually be kinetically and thermodynamically limited if you decide to pick the E naught of your CV. So actually, if I just did the CV of this, let's actually just do CV. So if I had CV, and if I let's just simulate this. So let me start at like minus 100 for an oxidation, and go to here. So if I simulated this and I get this, I should maybe start at like 0. Actually, that would make it look a little bit better. But if you're, that's the initial, and then the final will also be 0. But if this was my voltammogram, and you're like, oh, this is my E naught, my peak, you really need to be applying way over here to get the diffusion limited current. So that's the like accurate way of doing it. And then you may also want to do it because if you have solution resistance, because it looks like you still have solution resistance, even with just by from what you showed.
There's a follow up here. He said,
"Oh, you follow up."
The solution resistance. Just want to clarify: the solution is 1 molar KOH, 2.8 ohms when carrying EIS. So actually, it looks like the solution resistance is very negligible. If that's what you're saying, is this uncompensated resistance was 2.8 ohms? That's nothing.
Yeah, it's strange that you see such a large difference in peak voltage.
Yeah, that's odd. I mean, unless it's some really irreversible kind of thing going on. I don't know.
Yeah, like
pseudo reversibility. A change in the peak location based on scan rate is usually an indication of a lack of reversibility of your process, I think.
Yeah,
or solution resistance, right?
Yeah, so and you can tell here. I'll show you another thing. You can also, like, if you're worried, like, oh well, what process is it? We can simulate it. Like, we can actually simulate it. And if I go here and I'm like, well, if I have a more irreversible system, something with much slower kinetics, which could be your system, right? Actually, I'll make it very slow. You'll notice that, oh wow, I'm not getting a reverse wave, and the peak is shifting way over from my 0.55 volts. It's way shifted. And now I did like a bit of an extreme example, but like, so I get this kind of shape for kind of a slow kinetic as I'm moving forward. But now the thing that's interesting is I'm gonna archive this, and we can take a look at it later. But now I'm gonna actually do the same thing at a lower scan rate. So let's see if I do this at a lower scan rate. And actually, you probably just noticed it actually shifted over. So we can also compare those two things. So I'm going to archive that. I'll create a new plot, and then I'll just put these two. Let's see. Let's get the voltammogram.
I bet you got his kinetics perfectly.
I got your connects
Yeah.
super
Are
perfect.
they,
now.
is it 100 difference? Let's see. Did you get it like absolutely
Oh,
perfectly? Like his is 100 different. I wonder if you got it exactly
Oh
100.
no, I probably
You
did
just
get that.
perfectly predicted his kinetics.
Yeah, so
It's close.
so I'm gonna use this other tool. This is the crosshair. So this is about peak position here, and then if I do this nice crosshair tool here,
What do we got? We got
Get-
700 and it's so close.
it's so close.
You almost got the exact thing.
Almost exactly. But that's okay. So
that's pretty good though.
So this is pretty good. So this is another thing you could do, and you can use this tool that I'm using right now to actually look at. Because here, I'll do another thing just to kind of just to show you. Let's go back to this. Now let's say I go back to having very nice, very fast electron transfer kinetics, right? And we'll just like look at this. Like if I look here and then I change the scan rate, it shouldn't really change. Like it didn't change. The current went up, but like this didn't change. Now, if you had a lot of solution resistance, let's say if I had let's just put like 1,000 ohms. If I were to simulate that, it's going to stretch out my voltammogram this way, and this will change as a function of the scan rate. So if I simulate this, it becomes lower. So
yeah, this is a really excellent visualization of the thing that we just said, which is that the change in the peak location, the voltage of your peak by scan rate is basically one of two things, right? It's the uncompensated resistance, solution resistance, basically, or the kinetics. Right. And it's if you have almost no solution resistance, if what you said is you've measured accurately, and 1 molar KOH is quite
it's like 2 or
concentrated. 2 ohms is almost nothing unless you have a really high current. Right. Because IR, right? I times R, 2 ohms times a milliamp is a millivolt. At most you have a couple of millivolts. If you're in microamp current, it's like nothing, right? So the shift is negligible. Unless you have a really big electrode. If you have an electrode that you have like 100 milliamps, well, now you have 100 millivolt. That would explain it. Fine. Right. But in the absence of that, it just probably means your kinetics are poor.
And so you can and I just demonstrated it. So hopefully that gives you a little bit of help with thinking about this problem. And if you want to do CA, like you can simulate the CA as well. So
I put the link to our
it's Aftermath Live.
That's the software that Alex was just
showing
you, right? It's available online. You can go to aftermathlive.com. You can check it out. Look into getting a license or whatever. You can do this kind of simulation yourself. So check it out. I guess.
All right, good. I'm glad that you like the simulation, and it was very interesting, and hopefully it taught you something.
And I'm glad I'm an afterthought.
I know. It's also. Like and Neil also.
Yeah, me also.
He typed that in. That was just like and Neil. He just
I guess I'm sort of involved. Alex did all of the simulating and all of the work, but I'm just here. It's fine.
It's all.
I don't care. I'm barely contributing. I get it. It's fine. Don't worry. I know I'm greatly overshadowed by my colleague over here. That's fine. I don't need any recognition. It's fine. I don't care.
I care.
Oh, that's funny.
Let's see. So, all right. So we have another question from Manuel's. How recommended are electrodes made of PCB? I believe that's printed circuit board for measuring the proton conductivity of polymeric membranes. Are they accurate, or would there be a high degree of error?
Kind of depends. I mean,
a
PCB electrode, like I guess I don't really have. I don't have a good answer to that because I don't know what it.
What's the material?
Like a PCB is a printed circuit board. Like a circuit board is like, a silicon whatever circuit board's made out of, basically, and it's an insulator. The PCB itself is an insulator, and you have traces on it that are conductive. Like that. This is how like computers are made. Potentiostats. Like every electronic, right, is made with printed circuit boards, and that's just how they work. So it's like presumably. You're talking about like a chip, like a rectangle or a square circuit board with traces on it, like almost like a screen printed electrode or something, I guess.
Mhm.
I don't know. I have an answer for this. Like measuring the proton conductivity of polymeric, like,
So it needs to be selective, right? It needs to be selective for protons.
well, no, but proton conductivity of, yeah, that. Well, first of all, what I described earlier, I think in response to your first question, Manuel's, was like measuring the conductivity.
Mhm.
That's not proton conductivity. That's just like
Regular conductivity.
regular
Yeah.
conductivity, right? It's like Siemens per centimeter or something, I think is the unit basically.
Mhm.
And that's not, H pluses per hour, or I don't know. I'm not quite honestly sure how to measure proton conductivity as a quantity, as a property. I don't know how you would do that exactly. And that method that I described requires 4 electrodes, 2 of which are reference electrodes. So that's not a PCB. And then the other 2 electrodes are just any charge carrier. So usually you just use like a platinum mesh or a platinum coil of some kind, because you're actually just looking for something to complete the circuit. Basically, you're more interested in that potential difference from your reference electrodes across the membrane, because that's what allows you to know the distance between your measurement points, the L that I showed in that diagram, I guess. And the whether you use a platinum coil or a printed circuit board with some conductive material, like from that perspective, what I described before, I don't know that a PCB does any, like, I don't know what its purpose would be beyond just being a charge carrier
Mhm.
to get you the resistance
Mhm.
measurement that you're after.
Yeah.
I frankly, I guess I don't know. And if you have a follow up about what is this PCB electrode exactly, or what's the experiment you're talking about, and if there's a
Mhm.
different kind of experiment than what I'm described previously for like a proton conductivity, is this like a PCB that's, often with like a fuel cell test, you have your membrane, you sort of sandwich everything on the membrane itself, like your platinum, platinum on carbon or something like that. If you're doing like a fuel cell, you sometimes will press it into the membrane, or actually paint or spray it on the membrane itself, to minimize the distance. You minimize some losses, because basically at the anode to the cathode, right, you have the oxygen reduction reaction occurring at the cathode, basically. And so the protons are created right at the membrane. So they're right there. They travel through the membrane, and that's where you're measuring the product. But I don't know what like data is required to get you proton conductivity measurement, to be honest. And if that's a PCB like pressed on the membrane, like maybe that would work because it's like flat, you know what I mean? It's like flat, and I don't know, it's a
Yeah.
square, it's a rectangle. Like maybe there's something there. But beyond this kind of just me spitballing about it, I don't have any specific knowledge or information. And then, as I said, related to that sort of membrane cell that I talked about and showed you earlier, I don't know that that does anything for you beyond just the typical platinum wire mesh, electrode as a charge carrier, because that's all you really need.
Yeah, I'm also thinking that because he's also asking, are they accurate? Or would there be a high degree of error? I think to do that, you'd have to compare it with another technique that is either well known for measuring like proton conductivity,
Yeah.
maybe a pH meter or something like that. I don't know.
Yeah, I guess. Yeah, maybe it's like different pHs have different amount of protons, and how, I don't know what's I don't,
Yeah.
like
Well,
how fast are protons getting across? Like I don't. Are you measuring the like hydrogen evolution reaction at the anode, to
yeah,
determine how many protons are
yeah.
passing through, or I don't know. I'm just guessing.
Oh, I was just thinking about like, if you have a pH meter that's relatively accurate, you could look at like, well, it's kind of a direct measure of how many protons you have. And then if the pH is changing as a function of time between the membrane, that tells you a little bit of information about
That's true.
the content. That's maybe one
like-
way, but
Like
I don't
membrane
know.
on one side has no protons. It's like neutral water or something.
Yeah, yeah.
And as the pH changes, that's protons making its way
Radiant's
through.
making its way through.
I mean, that could work. I don't know where
Yeah.
that's not an electrochemical measurement though.
Mm.
I mean, the
Well,
pH meter is.
yeah,
an
the pH
but
meters, but
forget that part of it. I know you're
Yeah.
right, but like that doesn't use a PCB. There's no
yeah.
that part of it is kind of not.
Yeah, but if that was a method, and then you could compare it with like a PCB electrode. Usually, all these things need to be sensitive or selective for protons for you to make that kind of measurement. So, but I haven't used one or have seen one. So that's
And it's just a bit odd because like a printed circuit board, like I said, it's an insulating, silicon whatever chip or whatever, and then traces that are carry the current, and then the electrode or something, and it's like you don't always submerge the whole thing because you'll get like the traces in solution, and that's not always desirable unless they're well insulated or something. Like we make screen printed electrodes, for example, like at our company. It's like it has different parts to it, right? Like, and the whole thing is usually insulated with a dielectric material or glass or something like that, so that the traces and the other parts aren't exposed. And the only things that are exposed are the electrodes that you're looking to get information from. So like this a PCB electrode would have to have something similar to that. Like it'd have to be insulated around the parts that you don't want contributing to your signal because they're not part of the electrode. So using just like some PCB you bought at an electronics shop isn't always a good way to do electrochemistry because you have too much other stuff in contact with the electrolyte. And if it's conductive, it's part of the electrode now. And you don't want everything to be part of the electrode. You want what you want to be part of the electrode, right? So
let's see. We got
question. We got this question from Doolies, who we have seen before. Welcome back. Can you suggest any good papers that might show a solid example of performing a Levich calculation in a non-aqueous system? That's a good question.
And I don't know about any publications, but like we have videos on it. Like Neil has done a webinar on. That was aqueous, but still.
Yeah, I used aqueous for mine.
But I made a video on how to calculate the diffusion coefficient for an RDE, and I just have to find it.
Non-aqueous,
but it kind of goes through like the math a little bit more.
I guess my follow-up question is what about this analysis with non-aqueous is of interest, I suppose. Like the analysis is what it is. Like Levich analysis, is involves finding the diffusion limited current, right, and correlating that to get a diffusion coefficient, for example, plotting it versus differences in scan rate. Like whether you're in aqueous or non-aqueous is almost irrelevant, right? For the most part, as long as you know the critical components, like with the Levich equation, you're talking about I guess kinematic viscosity. I have to look at it. I'm looking at it now. So basically kinematic viscosity. So, a non-aqueous electrolyte is going to have a different viscosity, physical properties than water, but it is what it is. You need the Faraday's constant is what it is. You need the concentration of your analyte, which whether it's non-aqueous or aqueous, it's some number. The area of your electrode is some number. So it's like the Levich analysis, Kotecki, Levich, Tafel, for that matter, anything in aqueous or non-aqueous, like doesn't matter, right? Just as long as you are able to get a diffusion limitation. Now, I guess with respect to non-aqueous, sometimes the kind of funky stuff with non-aqueous compared to aqueous is that your potential window is wider usually. And sometimes if you have multiple processes, you can get like a lot of peaks kind of in sequential, like if you have a lot, I don't know, I'm just making up stuff. Like if you have like ferrocene as an internal standard, let's just say, and you have some, material you're trying to get your Levich analysis, if like the peak overlaps with ferrocene, you could have some interference. There's like stuff that could happen, but fundamentally it's the same.
Yeah.
right? You have a novel organic molecule. Eventually want to find how many electrons I can add to reduce it. Yeah, I mean, really, honestly,
Yeah.
your process is going to be the same as with oxygen reduction reaction or anything,
Yeah.
that you would do rotating experiments. You're going to look to get a plateau, even if it's like a short time before it does something else, because it's non-aqueous. You might have some other, I don't know, other odd processes that occur at some voltage. If you can get a plateau at
Mhm.
some potential, right? Change the rotation rate, get a different plateau, and you have cascading limiting currents, and you can do your Levich analysis. Like, I don't have any papers like off the top of my head or saved that I could recommend to you for this specific kind of a thing, but I'm sure you can find, and especially if you're in academia, we're not, it's harder sometimes for us to like get all the
Mhm.
different kinds of academic texts in literature access. Now working at a company, we don't have like SciFinder and all that kind of stuff, right? We don't have like subscriptions to the models like you do when you're in academia, to papers. But I mean, if you just search for RDE acetonitrile, I don't know, whatever, non-aqueous, you'll probably find hundreds of papers. I'm sure there's a lot of people that have done stuff like this. So
Yeah.
it doesn't, there's nothing intrinsic about the solvent that precludes Levich analysis,
Yeah.
right? As long as you know the properties of it and everything, you should be just as perfectly able
Mhm.
to do what you're describing. And yeah, you do your Levich analysis. You can get diffusion coefficient. You can do Katecki Levich and get Tafel. You can get get to that. How many electrons? That's more of a Tafel thing, right? You move to the kinetic information
Mhm.
to try to figure out how many electrons are transferred. But whether it's Levich or Katecki Levich and Tafel, certainly should be doable.
Yeah. 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 I think so. Santiago has another question. Is it possible to observe electrolyte decomposition with a CV? Yes. Yes, it is. So it depends on the system, depends on the solvent and other analytes and stuff like that. But usually the limits of your potential window are going to be where solvent, electrolyte, and things start to break apart or decompose. And so, like, what you'll see often is something like you'll see something I think a bit like this. So if you have your CV, voltage, current, maybe your potential window is just kind of within this range. But then if you go beyond it, you'll start to see like this or something like that. It'll just like go up into craziness, or it'll go down very sharply. And it's within some of these regions that your electrolyte, or your solvent, or your electrode, like a bunch of things can definitely decompose. And it's not always clear which thing is decomposing, but yes, there are times where it's like, all right, I changed the electrolyte and I'm all of a sudden like my potential window's different. Then it's like, oh, your electrolyte's the thing that's decomposing. So yep, that's the answer to the question. Like, it is absolutely possible to observe the decomposition of an electrolyte in
Yeah.
CV.
And actually, technically speaking, the oxygen evolution reaction and the hydrogen evolution reaction are electrolyte decomposition, right? In some ways,
Oh,
it's
because you're
like,
which one, the oxygen evolution?
yeah,
Yes, yeah,
right.
because
Like
it's water, right?
what you just drew in the um, case of like aqueous electrolyte
Yeah.
is the far right oxidation side is the oxygen evolution OER, right? That's actually decomposing the electrolyte to evolve oxygen. And the other side, all the way on the left, reduction, is the hydrogen evolution reaction. It's actually just both of those extremes of your aqueous electrolyte, water, is decomposing the electrolyte to produce oxygen or hydrogen.
Mhm.
So,
Yeah.
so there's a whole field of study on those, doing CV and other experiments to decompose the electrolyte to produce oxygen or hydrogen gas. Yeah.
Yeah. All right. Well, it doesn't look like there's any questions right now. We can hang out for a
This is
bit longer.
Julius was just
Oh,
comparing. Yeah,
Dua's
saying,
came back with
yeah,
another
one of the
thing.
issue you were having to find the viscosity of your solvents. Yeah. I think isn't a rheometer, is that a similar rheometer? It's like usually it's like a spinning, it's almost like it's actually like an RDE thing. But someone when I was in like an undergraduate was using one of these
Yeah.
things. It's like it measures the tension or the shear, so
Mm.
something right, something like that.
Oh,
And
okay.
it can measure that because that's basically viscosity. It's like viscosity is in
Resistance to flow.
yeah,
I
exactly,
think.
exactly. It's a resistance to flow. So it's like the way that that's measured, a viscometer or a rheometer, RHEO rheometer, I think. It's like it's some kind of like cylinder or disc that like spins
Hmm.
and it measures the shear. Maybe this is shear. Maybe it's not exactly the same measurement. But anyway, to measure viscosity, it's something like that. I think
Yeah.
that's in brief how like practically how you can measure that kind of thing is
Yeah.
you're measuring the resistance to something spinning in it or whatever,
Mhm.
and you know, so something like that.
Yeah, and then the kinematic viscosity is just that normalized to the density of your
Yeah,
material. So
yeah,
you just have to
viscosity
figure
over
that out.
density is kinematic viscosity, right? I think that's what
Yeah.
it is.
Yeah. And another way you could do it too, it's a little convoluted, but you could do Levich behavior on a known system where it's like, I know that the diffusion coefficient of this species is this, so I can use that as my known
To back out the
to back out the kinematic
viscosity.
viscosity.
Yeah.
It's a bit like roundabout, but
And it's also making the assumption that your diffusion coefficient assumption's correct.
yes, that it's the
Which
same.
is it? Who knows?
which
Yeah.
may or may not be.
Yeah,
So
yeah. So there's
there may be another way around it. It's a guess, but
yeah, I think that's a tricky thing though, is that probably practically once you're doing a lot of non-aqueous stuff,
mhm.
depending on what you're using, the tabulated like properties are not as easy.
Yeah.
You know, like
Not
if you're
as
using
good.
like, you know, DMSO with this much supporting
Yeah,
electrolyte and
CHI,
whatever,
yeah.
it's like, what are the properties? Like, I don't know, 3 people ever have used that. And no one's
Yeah,
ever,
they
you know,
haven't
you can't look
published
in
it.
your like, what is
Like a table.
yeah, some tabulated table of stuff. You have to like guess or you know make up, you know, whatever. That's the tricky part with using non-aqueous, I think, compared to water. Like water's so easy, right? It's like a centipoise viscosity and the kinematic viscosity is whatever the number is. You know, it's like easy. It's easily tabulated. You know,
Yeah.
whatever. It's easy to find properties of water or just make an assumption that's relatively accurate. And the properties of water don't change that dramatically. Like when you have a little bit of salt in it, you know, it's like the viscosity's
Oh yeah,
about the
it's
same or
basically
whatever.
the
So,
same. Yeah.
yeah.
It's true. It's true.
Those kinds of things become tricky when you're doing non-aqueous. So I mean, really, the answer is just use water. Like, why are you bothering with this non-aqueous nonsense? Like, it's a waste of time. Just use water.
Yeah, just use water for everything.
Water's everywhere. It's easy.
This novel organic molecule probably isn't happy in a lot of things. So,
Yeah, that's probably true.
yeah, please don't tell us that it's only soluble in toluene. I'm like, looks like you're not going to be doing Levich studies.
Yeah, I guess not. Yeah,
No,
toluene.
or
Yeah.
some other not very happy.
I think the worst part about using toluene, xylene, benzene, BTX, all that kind of stuff is that it's really smelly.
Yeah.
It's so like that aromatic smell. You know what I mean? Like it's like
Smelly in an organic chemistry lab. Get out of here.
I know, really, I know. It's like, are you one of those people that likes the smell of gasoline? I like the smell of gasoline. I used to like it, you know, like
Oh yeah.
It's-
There is something like kind of
it's like sweet smelling kind of.
yeah, sometimes it has that. But then like my brain is just like, this means that you're smelling like really bad chemicals and you need to get
Yeah,
go
like
away.
once I got old enough to realize that I shouldn't enjoy smelling this and I should stop trying to do that because I'm like breathing in
sniffing
dangerous
markers and
yeah,
stuff
or it's like when you
that
get a new
you're kidding.
car, you know, the new car smell, it's like that's
Yes.
just plasticizers.
Yeah.
It's not a good thing to be
It's not a good
smelling,
thing to be smelling, but
but but it smells good. So
it does smell
you know,
good.
it's like not every good smell you should be encouraging yourself to smell, you know.
Yeah.
But I mean, if it's there, you can't not smell it. What are you supposed to do?
Yeah.
Leave the gas station? Like I live here. I'm smelling gas now.
Yeah.
I don't live in a gas station. I'm kidding. Yeah, no, it is one of those things. It's some parts of me miss the research lab smells. I don't know. It's like there's something about it. Like not every smell was good, obviously, but like you know, there's just kind of the whole like you know, like the smell of acetone when you're cleaning glassware and stuff. Like Is this weird?
Just,
this weird?
I'm just thinking. I
Like
don't know.
isopropanol has a smell.
Yeah,
to it.
isopropyl has a smell. Like I worked with some pyridine. Pyridine has a smell.
I don't know
Like
what pyridine smells like.
I
I don't think methanol has a smell. It doesn't smell like anything. But isopropyl
smells like
does.
alcohol.
Oh, yeah, I guess
like a
it's
weak
just,
alcohol
I guess
smell,
just
but
general. Yeah.
yeah. Acetaldehyde has a smell.
I don't
wish you could use
think I
acetaldehyde.
know what acetaldehyde. I've used acetaldehyde only briefly. I used it a little bit. THF.
Gross.
Yeah,
I'm sorry, man.
THF is so nasty.
Add like 1 molar of your supporting electrolyte, then it'll work nicely. It'll be expensive, but
THF has such a miserable conductivity.
Yeah.
Like its conductivity, it's one of the worst. Like
yeah,
like the same molarity of supporting electrolyte in THF has like 10 or like 10x the uncompensated resistance
yeah,
as like acetonitrile.
yeah.
Right. It's like
it's crazy.
I've actually done this like relatively recently. I was just
Mhm.
it was with a friendly laboratory just doing some testing for some software we were making or something. And it was like, oh, let's just see what happens if we do like the same supporting electrolyte, like 0.1 molar, like TBA,
Mhm.
whatever, right?
Yeah.
In like acetonitrile, THF, like DMSO or whatever. And it's like THF, it was like acetonitrile, it's like, whatever, like 80 ohms, like not too much, whatever. And it's THF, it's like 1 kilo ohm. It's like just crazy.
Thousands. Yeah, it can be.
It's just
thousands of
crazy. Yeah, it's like
ohms.
the same amount of supporting electrolyte. It's like, oh gosh, this is the worst. Why does anybody use this? What a crummy position to be in. You have to use THF. It's a pain.
I was troubleshooting an issue with somebody using THF, and they were trying to use they were using positive feedback as a technique to try to measure
Oh no.
the solution resistance, and it's like it's not working, and it's like try going even higher.
Yeah, you're like I'm at 500 ohms. It's not oscillating.
Like,
Yeah, it's
yeah.
more.
It's more.
It's a lot more. So sad.
Oh yeah. But then but luckily they found it at like 2,000 ohms or something. I'm just
Yeah,
like,
that sounds about right. Between
that's-
1 and 2,000 ohms usually.
yeah.
It's like unless you have really small current,
Yeah.
your IR drop is substantial.
Yeah. It's very rough.
Yeah, I heavily sympathize with people who have to use THF and
Yeah.
some of those really nasty non-aqueous solvents. I mean, the only good thing is you can go like plus or minus 9 volts and it doesn't
Yeah.
fall apart. It's like so stable, right? I mean, that's
Yeah.
part of the benefit. Like water, you have like a volt to work with, so that's it.
Yeah. that's
THF,
true.
you have like 5 volts you can work with, so it's
Yeah.
nice.
There's also just more organic molecules are soluble in THF.
Yeah.
Some stuff is just not soluble in like DMSO or
Yeah. Not all of them
or,
work
acetonitrile.
quite well. Yeah, acetonitrile is the like closest to water, ubiquitous.
Yeah.
But not everything really dissolves in it very well.
Yeah, no, that's true. We have a comment. It just says,
Yeah, is this a question or did you have a follow-up?
yeah, it just says scaling and dimensionless equations.
So, I mean, dimensionless variables and dimensionless equations are useful. I don't know if you have a specific question about it.
Yeah.
You know,
I
things like the Reynolds number, Prandtl number, and Rayleigh number. These are interesting. A lot of empirical.
radians.
Yeah, radians. a lot of our sort of fundamental stuff like some rotating, like the Heisenberg equation, like it's like
Oh.
corrosion rotation stuff, are empirical relationships based on dimensionless quantities. A lot of that, some of the like RDE, like Levich and Kentucky, is based on first principles and geometry and whatnot. But there are some analyses that you do with like cylinder electrodes, for example, that work based on you look at the equations and stuff, and it's like Scantle number to the 0.71 power and some crazy thing. It's like
Scantle number?
yeah.
What's the Scantle number?
Let me look it up. This is a
This is
difference.
this is like the time I told you about steer radians, and you're like, "What's a steer radians? Not a real thing." Well, I guess it is.
Wait, it's not Scantle. That's not it. It's S. Is it Schmidt number? What is it? SC. Schmidt number.
So yeah, Schmidt number.
You know what I did? I combined Schmidt and Prandtl.
Oh,
And I said Scantle.
Wait, what's Prandtl?
So the first of all, the Schmidt number,
Schmidt
SC,
number. Yeah.
it's kinematic viscosity.
Mm.
What is it? Hang on. The Schmidt number is it's viscosity over diffusivity. It's mu over rho d. So it's viscosity over density times diffusion coefficient.
Okay.
So it's viscosity over mass diffusion. So it's a relation. All these different numbers are just different variations of like the viscosity, the relationship between the ratio of viscosity and diffusion, or the relationship of like density and flow. It's whatever.
Yeah.
The Prandtl number is, let's see. That one is, I think density is involved. I did all of these when I was in undergrad. Prandtl number is momentum diffusivity over thermal diffusivity. So it's Cp mu over K.
Interesting.
So it's the specific, specific heat times viscosity over the thermal conductivity. It's like a heat. It's a heat transfer. So it's like when you do these or whatever, what it allows you to do is normalize properties of different materials. So it's like you have steel and magnesium and cobalt and all this kind of stuff. They all have different like specific heats, and they all have different like physical properties.
Yeah.
And so when you make like a Prandtl number, they all have a Prandtl number, right? And then it's like two materials can have a similar Prandtl number, so they have different specific properties or whatever, but like their Prandtl numbers, so they're going to behave similar in certain situations. And then they use these Prandtl number and this Scantle and the Prandtl and Schmidt. I said Scantle. Schmidt.
Schmidt.
There's a Rayleigh number. Reynolds number. Most people know
number.
Reynolds number. Reynolds number is dV rho over mu.
Yeah.
Most people know Reynolds number because it's just basically a descriptor of flow of fluid, and it describes whether it's laminar or turbulent. So we're familiar with that one. Reynolds number is just another dimensionless number. That's all it is.
Yeah.
And so you can correlate behavior with a lot of these dimensionless numbers. They're kind of, as an engineer, I did a lot of this in undergraduate.
Absolutely.
A lot of flow chemistry uses these, and a lot of thermodynamics as well. So
nice.
Thanks for your comment. I got to wax on about fake numbers like the Scantle number.
The Scantle number.
Prandtl, Scantle, Chantle, Schmidt, Rayleigh, Reynolds. There's like a few dozen of these that are used pretty regularly.
Yeah. So we just got a question from Josh Wolf. I'm interested in growing geobacter bacteria on a modified carbon anode. How might I measure different materials for their connectivity to the bacteria? Like, do you mean how is the bacteria stuck on the surface or not, or irreversibly absorbed onto the surface?
For their connectivity to the bacteria, yeah. So
connectivity.
So first of all, you're going to have to know. Well, I guess how? Yeah, right. Like you said, how are you? How is the bacteria adhering to your anode, your material, right? If it's just growing on it, like it's an organism, so it's like, is it just, I don't know, like physisorb, chemisorb, like how, I don't know. I don't know bacteria very well.
This is like a Shelley Mintier type of question.
Yeah, would she have biological? I don't know a lot about like biological material. Like how is a bacteria, like if you grow bacteria on carbon, and then you have this carbon material, and there's bacteria just hanging around on it.
Yeah.
And then you take that electrode and you put it into a solution to do electrochemistry. Does the bacteria fall off? Does it stay on?
Yeah.
So that's an open question. Like, to be able to get measurements, first of all, you have to know they are electrically connected by electrical pili called nanowire. Well, so you have nanowires, but again, it's like, I guess that's the first. So the first part answer to your question is related to the intrinsic knowledge that the bacteria is there and how much of it is there. They reduce Fe 3+ to 2+ in the wild. Interesting.
Cool.
Okay, that's kind of cool.
That's pretty neat.
So first of all, let's just assume the bacteria. Like if you grow bacteria and you grow the same amount on a bunch of different materials, right? The simplest answer is do impedance, right? Do impedance at open circuit and measure the resistance. If you have nothing Faradaic happening, you're just going to get kind of a straight line. You're going to get some capacitance. You might have a small semicircle and then a diffusional tail or something like that. You can just kind of see, for example, like you have 3 different, anode materials, carbon materials, whatever. The highest resistance is the worst one in general, right? You might have something where it's like the material that has the really like low resistance means it has a good performance, a strong adhesion with the bacteria or something of that nature. Might be a one way to tell. Generally speaking, that's kind of a good way to do comparisons between different materials is check the resistance, right? Like,
yeah.
but I don't know.
I mean, do the bacteria do electrochemistry on an electrode? Like you say that they reduce iron 3 to iron 2 in the wild, but
so are they doing that
do
on
they?
your carbon?
Will your electrode detect that reduction reaction? Like if you put the bacteria on the electrode and then you feed it iron 3+, will you start to see reduction currents start to happen?
Or
do
you have to polarize the electrode?
You have
to
to
get
polarize
that?
it. You may need a sacrificial reagent, on the other side, for the counter electrode. But like if you can do it electrochemically and you get a response, then I would just repeat that response on other electrodes to also measure like, oh, I didn't get as much. I did the exact same growth procedure for putting the bacteria on it. And if I get less of them on the surface, then that should be indicative of how much of the bacteria is connected to the platinum or whatever.
So like comparing the currents you get would be indicative of like more or less of that reduction occurring, which would indicate how well the bacteria is hanging around to do its thing.
Yeah.
So resistance, current, some of these sort of simple electrochemistry diagnostics might help you kind of determine how well the stuff is there, how well it's sticking. I don't know if there's any other thing that might happen. Like for example, again, I'm just guessing here because I don't have a lot of knowledge of like biological kinds of systems, but like if you heavily polarize the electrode, does the bacteria die? Like if you go, like does the bacteria, like if you go like up a volt, does it just zap the bacteria? Does it kill it? Like, or like down, I don't know. Like does the bacteria itself something oxidize or so you could like look for a peak of bacteria death. It's like
peak of bacteria death.
Yeah, like what if you like oxidize the anode, and you get a peak, and that's like the bacteria oxidizing and dying.
Yeah, I know.
I don't know. What if it's kind of morbid, but it's just bacteria.
Oh yeah, it's bacteria.
Like killing the bacteria that's present and getting some electrochemistry results for it could be an indication of how much is there.
It's like anodic stripping sort of.
Yeah, except it's killing bacteria.
Yeah, instead of taking like lead off a surface or something.
They die at see, I'm right. They die at 700. Thank you. See,
so they die at 700.
Josh is with me. Well, that's right. We're killing bacteria together, Josh.
I wasn't saying that they don't.
I said it, and you're looking at me like I'm a murderer. Like how could you kill bacteria?
Oh, you're not a murderer. Josh Wolf is a murderer.
That's true. I have not done this, but
he has not killed the bacteria. Just messing with you, man.
Oh, that's funny. Yeah, I mean, I suppose it's like if you have like death electrochemistry experiments, it should have some current associated with it, I suppose. Like if
this is the thing that I find interesting is like bacteria is so much bigger than all the like redox molecules and stuff that we deal with.
Is it really? Oh yeah, then the molecules.
Just like there's a cell, there's like a cell membrane, and then there's all the stuff inside of the cell, and it's probably like microns in size. I
Yeah,
want to
think,
say,
I think
like,
so.
let's see, size.
Bacteria is microns, I think.
Yeah, size
pretty big.
of a bacteria.
Like 1 to 10 microns. Something
Yeah,
like
1 to 10 microns. That's right.
Oh, that really? Oh,
Yeah,
that's
yeah,
so
that-
good.
that's
I just that was a total guess.
Yeah. Bacterial cells range from 1 to 10 microns in length and 0.2 to 1 micron in width. I wonder how high they are. I mean, they're three-dimensional, right? So
They're only 2-dimensional.
they're only two.
That's right.
I guess that explains why we could do electrochemistry.
That's right. It's 2-dimensional. It fits all of our equations just perfectly. Bacteria are not 3-dimensional.
Oh god.
Oh,
That is funny.
yeah.
Well, hopefully that was helpful, Josh.
Yeah. So kill them and then figure out how much current is responsible for killing them, and then you'll figure out how well are they stuck or something.
Yeah. Add known quantities of like
And then hopefully you can sleep at night with your
iron.
decisions.
Yeah.
You know.
Any advice for building an impedance measuring device or potentiostat with a Raspberry Pi that is modified carbon working electrodes?
Building a potentiostat. Yeah, I mean, I can't speak to that. Like we work for a company that we make potentiostats, and it's certainly possible to make your own.
But like impedance measurement.
Well, you're gonna have to.
That's
you're gonna
hard.
have to get some kind of a chip that can do frequency response.
Yeah.
Kinds of signals. You know, you need a chip that can apply fast sinusoidal pulses, and then making your own is a really, especially for impedance measurements, you will not likely have easy time doing that. Like, I can tell you, as again, someone who works at a company that makes potentiostats, and when I say we, I mean like our colleagues. Who are
the
much
engineers.
better. You know, we're not electrical engineers. We're just
Yeah.
electrochemists. I'm using the machines.
Yeah.
I have much smarter colleagues who make it, and it is not trivial to not. I mean, you can get a chip that'll do whatever, apply a sine wave or something, and it's like that is just the start of it. You have to,
and they gotta measure that.
You got to measure it. You got to analyze it. You got to filter it. You know, the accuracy is horrible at best without a lot of work. You know, it's definitely more possible to build a DC machine. Like that's doable. There's a lot of folks that make their own potentiostats. Even those are, to be honest, also quite inaccurate. You know, you get a lot of noise and a lot of messiness with the signal, especially if you're doing smaller currents and signals and things like that. And in your case, if you're doing like bacteria stuff, it's probably smallish, small signals. Cause I mean, it's a micron. It's pretty big.
Or they're not very like active. For
like how much current are you really expecting to get? So it's like the smaller the current you're looking to get, the more inaccurate your signals might be. And building your own potentiostat is definitely possible, but really not for the faint of heart, I guess. It's
in particular for impedance.
Yeah,
like
especially
for
for
impedance in particular, and then you have to write software, right, to control it. So which your Raspberry Pi probably can, but
I'm not sure the Raspberry Pi can do impedance, can it?
Well, no, I just mean like write software just for DC, for DC stuff. Like the potentiostat can do stuff, but you need to measure the data that's coming out, and like you want to write, you'll need to write some software to do that. So
buy a cheap buy a cheap frequency response analyzer. It's my suggestion. Buy the cheapest little portable one you can find or something, maybe a few $1,000 or something. And that'll probably get you started. You'll probably spend so much time trying to make your own and then questioning whether it's accurate or not. And by the time you get through all of that, you might as well just buy one. So unless I understand, maybe you can't afford it or there's other impediments. I understand. So Well, I guess we're gonna call it, are we?
Yeah, I think so. We've been going for about 2 hours.
Yeah,
just under. So I think that's good.
Yeah, thank you all for joining us again today. And as I said, if you're watching this live or after the fact, at some point, we're going to have a repository of all the questions that have
Oh,
been
yeah.
asked over the last 40 some odd episodes or 30 whatever episodes. I'm going to try to compile that and get that into a usable form. I don't know how or what form that'll be, but I promise I will do that at some point. And we'll keep adding to it every week. And that's the problem, is the longer I take to do it, the more questions I have to keep adding, because we do more of these
okay.
episodes. But yeah, well, anyway, thank you everybody for joining us yet again. And I guess we'll see you next week.
Yep. Yeah, we'll see you next
Take
week.
it easy, everybody.
Take care. Bye.